Welcome to the second video in our discussion of chemical kinetics. The previous video, linked in the description below, showed that the study of chemical kinetics was based on the study of the rate of the reaction. In general, the rate of anything is how much that thing changes with time. So for a reaction, the rate is going to be the change in concentration in terms of time, generally written as the change in molality, dA, over dt. The first thing to note is that rates of reaction are relative to the balanced equation. A simple reaction, hydrogen plus iodine goes to 2Hi, demonstrates this. As I am using hydrogen, I'm using iodine at the same rate because the reaction says 1H2 will react with 1I2. This is not going to be equal to the rate that the concentration of hydrogen iodide is changing, however. First of all, Hi is a product, H2 and I2 are the reactants. So as one side goes up, the other side goes down, the rates are going to be related, but opposite. So if I'm saying H2 and I2 are positive, the change in Hi is going to be negative. Secondly, the balanced equation says I make 2 HIs for every 1 H2, or put that another way, for every 1 H2, I make a half of a product. So the rates are related 1 to 1 to minus a half. These are what are called instantaneous rates, or the change in concentration with the change in time. Looking at that reaction in further detail, it's fairly obvious that at the start of the reactant, you have reactant and no product. As time goes by, the concentration of reactant is going to go down, while the concentration of product is going to go up. It is also going to go up at twice the rate since it's a 2-to-1 reaction. Main point is that this is not linear. This is important that the instantaneous rate is not linear because it's also non-predictive. The entire point of developing kinetics was to understand reactions so that companies could make money by exploiting them. If you're unable to predict what's going to happen, you will no longer have a reaction and you will no longer make money. Chemical kinetics started, and that study is based purely on experimental data. Essentially, chemical kinetics is the purest example of the scientific method that one will find. One runs reactions and observes them, hypothesizes as to why the reaction occurs the way it was. You'll see tests that reaction, that hypothesis, by running the reactions under various conditions, and then concludes about the rate and the mechanism. All chemical reactions, they are defined kinetically by a rate law. The rate law is identical for every reaction. R is equal to K times A to the X. This is based on experiments. The rate law is a linear fit of the nonlinear experimental data. A, in all cases, is going to be the concentration of reactants because that is the only thing that you know. So within this equation of the line, where A is your independent variable that you can change, you have two other constants. K is called the rate constant. From the experimental data, this is simply the slope of the line that you get. In nature, numbers do not show up randomly or for no reason. If one reaction has one slope and another reaction has a different slope, there's a reason behind that. That reason falls under theoretical, and you will find out that that has to do with how each reaction changes with temperature. X is called the order of the reaction. Experimentally, it's the parameter that gives you the straight line. For any given curve, if you raise it to the second power, first power, zero power, you can straighten out the line. Theoretically, again, the number doesn't come out of thin air, it means something. The order of each reactant tells you a great deal about how the reaction occurs, about the mechanism. So, what is a rate law? Here's a simple reaction. NO2 plus CO goes to NO plus CO2. The simple answer to what a rate law is, in this case, is that the rate is going to be equal to some constant times the concentration of NO2 to the x plus CO to some power y. You determine this experimentally once again. You will notice that this particular rate law has three unknowns in it. The rate is equal to k times a variable to the x times a variable to the y. You can't solve one equation with three unknowns, so you will need three equations, or in this case, you will need to perform three experiments. X is the power of NO2, so you will need to vary the amount of NO2. Y is the power of carbon monoxide, which will also have to be varied. So I choose one set of parameters starting at 0.1 molar each, and I measure a rate of 0.0021 moles per liter per second. To properly conduct an experiment, it's important to change only one variable at a time. So I opted to keep the carbon monoxide concentration constant and change the NO2 concentration to 0.2 molar, and the rate increased to 0.0084 moles per liter per second. Third experiment. Since I kept carbon monoxide constant first, for the third experiment, I now hold the concentration of NO2 constant and change carbon monoxide up to 0.2 molar, and I get a rate of 0.0083 moles per liter per second. These three equations allow me to solve for three unknowns. For example, if I want to solve for x, x is the order with respect to NO2. If I'm interested in NO2 only, that means the concentration of carbon monoxide has to stay constant. That happens in experiments 1 and 2. If I compare the rate of experiment 2 to experiment 1, 0.0084 to 0.0021, that's going to be equal to, for experiment 2, k times 0.2 to the x times 0.1 to the y. Experiment 1, 0.0021 is going to be equal to k times 0.1 to the x, 0.1 to the y. I still have three unknowns, but now it doesn't matter because k divided by k will cancel. 0.1 to the y by 0.1 to the y will cancel. And I get R2 of R1 is equal to 4, 0.008 over 0.002, is equal to 0.02 divided by 0.1 to the x. So 4 is equal to 2 to the x. I've now solved for x. X is 2. After I solve for x, I solve for y. Y now is the order with respect to carbon monoxide, which means the NO2 concentration has to stay constant. That leaves me with experiments 2 and 3. The rate of 3 over the rate of 2 is essentially 1, is equal to 0.02 divided by 0.01 to the y. Y winds up being 0 because anything to the 0 power is equal to 1. So now I've solved for x, I solve for y. The last thing to solve for is k. K is a constant. It's called the rate constant, which means it will not change. You are totally free to pick any given experiment. So in this case, if I just chose experiment 2 randomly, I get 0.0084 is equal to some constant times 0.02 squared times 0.01 to the 0. K gets a value of 21 for this reaction. So I have a rate law of 21 times NO2 squared times CO to the 0, or the rate is equal to a constant of 21 times the concentration of NO2 squared. You will notice that this does not depend upon the concentration of the other reactant, carbon monoxide. This has to do with the mechanism, which will be shown in the following video, also linked below. So, for any given reaction, you can solve a rate law by running several reactions, changing one variable at a time. The rate law is a measure of the change in concentration versus time. As previously mentioned, time is money. The entire point of studying kinetics and knowing the rate is to determine how much time it will take to do a given reaction. In order to do that, you have to do math. You have to do what's called an integrated rate law. What is the solution of the integral of concentration divided by a to the x versus the integral of k dt? With respect to order, if x is 0 and I have a 0-order reaction, the change of a over a to the 0 is simply going to be a1 minus a2. The change of k dt is going to be kt. So the integrated rate law for a first-order reaction is your original concentration minus whatever concentration is left at time t is going to be equal to kt. First-order reaction, the integral of 1 over x dx is going to be the log of a0 over a. The integral of k dt is still equal to kt. A second-order reaction, the integral of 1 over x squared is 1 over a minus 1 over a0. Once again, still equal to kt. The advantage of the integrated rate laws are also experimental. As seen, the right side of the equation is always equal to kt, which means you can simply observe what interpretation of the data gives you a linear response. If, for example, concentration versus time gives you a limited response, it means you have a 0-order reaction. If the log of concentration versus time gives you a linear response, it means the reaction you're looking at is first order. If the inverse of concentration versus time gives you a linear response, that means the reaction that you are looking at is second order. Another shortcut to determining what the order of a given reaction is to look at the half-life. Literally, the amount of time it takes for the original concentration to drop in half. These vary for all the orders. For a 0-order reaction, you will get a half-life of a0 over 2k. For a first-order reaction, since it's a logarithmic relationship and the concentration is being cut in half, a0 over a is going to be the log of 2, you will always get a half-life of 0.693 over k. For a second-order reaction, the inverse reaction, the half-life is 1 over a0k. So practically speaking, you monitor the reaction, determine when it was halfway completed, and it will fit one of these three relationships. Whichever one it fits tells you if the reaction is 0-order, first order, or second order. So the experimental data allows you to find the rate law. From the rate law, all information arises, specifically the order and the rate constant. The following video in this series, also linked in the description below, will look into how mechanism is determined by looking at a rate constant. And I hope you've enjoyed this video and found it useful. Thank you very much for listening.